Hello, in previous studies we have already drawn some simple pictures for studying de Broglie waves in the potential well and both traveling and stationary de Broglie waves for electron diffraction in crystals. It seems absolutely obvious that the particle itself and the traveling de Broglie wave corresponding to the particle fly together with the same speed. Surprisingly, that's not true. An electron from an electron gun outflies its own traveling de Broglie wave. To understand how this is possible, let's take a closer look at moving de Broglie waves. As a rule, periodic traveling waves are described by sine and cosine functions and their combinations, including so-called complex exponential function introduced in my previous story. The stationary cosine function has the form shown in the figure. Here k is the so-called wave number, and the argument of the periodic cosine function is so-called phase, that is kx. In our case, wavelength lambda is the distance between the nearest similar points. It is equal to 2 pi over k. In a moving periodic wave, the phase of the function depends on the linear combination of coordinate and time, that is kx minus omega t, where omega is angular frequency or just frequency. The speed of the wave can be determined by monitoring the movement of a point with a constant phase, for example with the phase kx minus omega t equal to 0. From this we get that the position of the point of constant zero phase changes in time according to the law x is omega over k multiplied by t, that is, its speed is omega over k. This speed is often called the phase speed of the wave or just the speed or velocity of wave. Together with discussed cosinusoidal waves, we often see sinusoidal traveling waves of the same argument kx minus omega t. Both waves have the same shape and phase velocity, but the sine wave is shifted relative to the cosine wave by a quarter of the wavelength lambda, or by value of pi over 2 in phase units. Then our waves are flying to the right. To get other waves flying to the left, you need to replace kx with minus kx. Now we will move from abstract traveling waves to de Broglie traveling waves applicable to atomic particles such as electrons. First of all, it is necessary to take into account that the concept of the de Broglie wavelength is well defined in physics, but the concept of the de Broglie wave itself is not specified precisely. We will call de Broglie waves any quantum mechanical wave functions that explicitly or implicitly use the formula for the de Broglie wavelength lambda 2 pi h bar over mv instead of solving the Schrödinger equation. Note also that I widely use such terms as wave function, probability wave, and de Broglie wave in my stories. I do not like and almost never use such a commonly used term as the matter wave for these objects, at least for the non-relativistic case, because in my view it confuses the concepts of the particle as a mass carrier and this quantum wave function, which is extremely bad. Further, any time-dependent functions are always complex functions in quantum mechanics. There are no exceptions to this rule. This is because only the secondary space change of the primary space change of the real part inspires the time change of the imaginary part of the wave function, and vice versa. For this reason, two functions or two parts of the time-dependent wave function are strongly needed. Quite similar mechanism works in electromagnetic waves describing photons. Space changes in electric field generate time changes in magnetic field of the electromagnetic wave and vice versa. We write two Maxwell equations corresponding to the time evolution of the electric and magnetic components, and after transformation we obtain two separate solutions for these two components of the electromagnetic wave. Similarly to this, we could also write two separate real equations for the two components of the wave function, but instead we write only a single time-dependent Schrödinger equation with directly incorporated imaginary unit and apply this equation to the complex wave function having real and imaginary components. Incorporation of imaginary unit I directly into the base equation has no certain physical interpretation. It is just a NUC math trick that allows us to shorten and simplify subsequent calculations. So, like any quantum wave function, the traveling de Broglie wave for a free particle must consist of two functions, and one of them must be labeled with an imaginary unit I. As you might guess, these functions are cosine and sine. By applying so-called Euler's formula described in my previous video, the wave can be represented by a complex exponential function. Very important note, the wave number k and frequency omega cannot have any value in the Broglie wave. They are strictly connected with the speed of the particle and its mass, as we will discuss a bit later in this video. As we have seen in my previous video, this wave can be visualized using cosine and sine curves traveling in two perpendicular directions, or as a running or spinning helix. We see similar but moving pictures for traveling de Broglie waves. In our real three-dimensional world, these waves are one-dimensional waves. They spread strictly along one line, coinciding with the x-axis. The two perpendicular directions that are used in visualizations are not the coordinate axes of our three-dimensional space. These are the axes of an imaginary complex plane. Our visualization mixes the real x-axis and two abstract axes of the complex plane. Honestly, in the real three-dimensional world, the complex exponentials should collapse, and we should see an infinitely thin striped line crawling along the x-axis. To obtain a three-dimensional de Broglie wave corresponding to one free particle, we must perform a very simple transition, write the same formula but apply it to the three-dimensional psi function, depending not only on x but now on x, y, and z. The entire three-dimensional space will be filled with infinitely thin striped lines flying parallel to the x-axis, and we will see a picture of flying planes. The object we see now is called the traveling plane wave. Of course, we can pull out individual striped lines from this object and expand them in additional abstract coordinate systems consisting of the x-axis and complex planes. Note that we get very similar pictures for electromagnetic waves, but in there, when expanding the lines, we plot vectors of the electric and magnetic fields along real axes parallel to usual space axes y and z. Very often plane waves are drawn not as moving spatial planes, but as lonely lines with expanded periodic waves, as we just did. In most cases, it is much easier and more convenient to use even more simplified two-dimensional symbols, such as the wavy curve and the other shorthand images shown in the figure. In the pictures, we see the Broglie waves and the electromagnetic waves moving to the right and left. For electromagnetic waves, directions of movement are determined by the right-hand screw rule. If the fingers of the right hand curl around from vector E to vector H, then the thumb shows the direction of the wave. Note that our eyes feel the electric field and do not feel the magnetic field of light, treated as an electromagnetic wave, and therefore the electric field E is considered to be the main or the first one in this rule. For the Broglie waves, we should use another algorithm that I call as the real fall rule. We need to choose a section of the wave where both the real and imaginary parts of the function are positive on complex axis. Then the direction of wave motion coincides with the direction of the real part decrease. Note that axes x, y, and z for electromagnetic field and real psi, imaginary psi, and x for wave functions should form right-handed coordinate systems. If you curl right fingers from x to y, then the thumb shows the positive z. To define positive x direction, we should curl fingers from y to z. If you curl fingers from real psi to imaginary psi axis, then the thumb shows the positive x. In the general case, the formula for the traveling plane de Broglie wave contains the scalar product of the so-called wave vector k and the position vector r of the observation point. Of course, absolute value of k is the above-mentioned wave number. By definition, the scalar product is equal to the product of the absolute values multiplied by the cosine of the angle between the vectors. From this condition and from the picture we see that the surfaces of the same face of the wave are planes perpendicular to the vector k. In other words, the equation describes the plane wave flying in the direction of vector k. As we have written many times in previous stories, for a particle of mass m flying with speed v, is the Broglie wavelength lambda is 2 pi h bar over mv. From here we can easily determine the wave number k as 2 pi over lambda, or mv over h bar, or p over h, where p is so-called momentum. Now important new idea. For a photon, its energy epsilon is related to the frequency of corresponding electromagnetic wave. By Planck's formula, epsilon is h bar omega. Similar equation is used for mass particles within concept of the Broglie waves. E is h bar omega. But energy E of the free electron is mv squared over 2. Then we have omega equals mv squared over 2h bar, or omega is h bar k squared over 2m. Phase velocity of the Broglie wave is omega over k, or half of the particle velocity v. This is a paradoxical fact. A particle outraces on the Broglie wave. We accelerate an electron in an electron gun, then the electron flies forward and the probability wave remains somewhere behind. How is this possible? Of course, the first suspicion is that we use wrong k and omega in the Broglie waves, but it turns out that our waves satisfy the Schrödinger equation. You can check this easily if you know how to calculate derivatives. Otherwise, you can check the starting out from definitions of derivatives as shown in this slide. This proves that we are using correct parameters and correct waves. By the way, we just demonstrated one more important rule. In order to satisfy the Schrödinger equation, the energy-time part minus I omega t in a complex exponential quantum function must always have the minus sign. Then perhaps we could establish some sort of unfolding clause for the wave function, for example, use some kind of Franz or moving boundary conditions. But unfortunately, no reasonable scheme for deploying the function can be invented for different reasons. Without going into details, we will only point out that in order to fix all the issues that arise, there is only one option left. Water rings from a thrown stone have a wave front coinciding with the very first ring. The Broglie waves related to free atomic particles are infinite by definition and do not have fronts. They appear like sea waves in calm weather simultaneously from horizon to horizon as soon as the wind begins to blow. In all calculations, we should assume that wave functions for free particles have been unfolded instantly and in an unlimited region of space before we began to consider the particle. The cost of this approach is that quantum mechanics imposes special empirical restrictions on wave functions. The wave function of any particle occupies the entire infinite universe, we may say from the star Arcturus in the north to Canopus in the south. It is continuous everywhere. It is equal to zero inside absolutely impenetrable obstacles, such as infinitely high potential walls, as we have already discussed in previous stories. The graph of the wave function may have kinks at the boundaries with absolutely impenetrable objects, provided that the function itself is still continuous. In all other places, including poorly penetrable obstacles, the function is smooth. Finally, it may expand and collapse immediately in the entire universe in case of some interactions with other objects. In the following discussions, you will see how important these rules are. I would like to emphasize that the electron as a carrier of mass, charge and spin is a real physical object localized in a very limited area in space. It cannot be on Earth and somewhere in a remote corner of our universe at the same moment in time. The electron is localized somewhere near our electron gun and flies inside the electron beam emitted by the gun in our example. In contrast, the wave function is not a real material object. We cannot detect it. It is just an element of a mathematical model controlled by the Schrödinger equation. The wave function must be infinite in space and satisfy the other requirements listed here. Otherwise, the mathematical model will not work. Today we understand and accept these unusual properties of the wave function, but when Schrödinger invented his equation, this was not clear. The fact that a free electron outflies its own quantum wave amazed physicists 100 years ago. Additional attempts to mitigate such an unusual situation with instant infinite de Broglie waves were associated with the ideas of using so-called wave packets, which could provide localization of particles in space. We will discuss these approaches in next videos.